Si us sembla, començaríem. Moltes gràcies per ser aquí. Distinguished colleagues, students, friends, and lovers of knowledge. Today, in a way, at the University of Girona, we are celebrating 100 years of quantum physics. A century since a new way of understanding nature transformed science, technology, and our vision of the universe forever. What began as a series of unsettling questions about light, matter, and energy ended up opening an intellectual landscape as astonishing as it is challenging. The ideas born in the laboratory and in the minds of pioneers such as Planck, Bohr, Heisenberg, and Schrödinger continue to shape our present, from quantum computing to precision metrology and the new information technologies. However, our purpose in this new series of our Ferrate-Moro lectures is not only to celebrate what has been achieved, but also to inspire the curiosity and critical spirit that have always driven physics and philosophy. That is why we are so pleased to have with us today Professor Adán Cabello, one of the most brilliant physicists in our continent and an eminent figure in the field of quantum physics. Last June, on the deck of a ship carrying several hundred physicists to Helgoland, that island in the German North Sea where the foundations of quantum physics were laid, Adán Cabello wrote the following, I quote, "We are here happily celebrating 100 years, but in reality it is a mess. They gave us this theory and we still don't understand what it's trying to say." End of quote. Fortunately, we have him here today to help us face the problem. Before concluding this brief introduction, I would like to explain that these Ferrate-Moro lectures could not have been carried out without the guidance of Michael Feixas, Director of the Chair of Information and Computation at our university. This seminar is due to him. Michael, moltes gràcies. I would also like to thank Professor Matthias Kleinman from the University of Siegen for being here with us today. Last but not least, of course, my most sincere and enthusiastic gratitude to Professor Adán Cabello for all the help he has given us in organizing these lessons. Professor Cabello, we are very, very honored by your presence, and without further delay, I give you the floor. Thank you.
Thank you very much for the introduction, John. It's an honor for me to be here and to talk about quantum mechanics in front of you. And the series of lectures will be, it's more an experiment than that series of lectures. We will be very, very ambitious in the sense that we will try to do something that is supposed to be impossible, meaning understanding quantum theory. 2025 has been declared by the United Nations the International Year of Quantum Science and Technology. Because, as John mentioned, 100 years ago, something happened. Quantum mechanics was born. Quantum theory is supposed to be the most useful and powerful theory physicists have ever devised. And everything started, in a sense, in a small island in the North Sea, Helgoland, in June 1925, because a young man, Heisenberg, 23 years old, had a high fever attack in his university in Göttingen. So he tried to solve the issue by moving far away from the spring and moving to this island. And there he spent 10 days. And during these 10 days, there's little to do in Helgoland. As you see, it's a very small island. So he worked basically all the time in solving a problem. And the problem was the following. It's a fundamental problem, and it's related to this experiment. When you shine light, a beam of light, into a prism, white light, you have, by dispersion of light, all the rainbows. However, if instead of white light, you shine the light coming from a source of excited atoms, a gas, for instance, hydrogen, then instead of seeing the whole rainbow, you just see some particular lines. Okay? In addition, you can put a source of white light and put the hydrogen in the middle, so it's absorbing some light. And then what you observe is what is called the absorption spectrum. In both cases, this set of lines is giving you a signature with this characteristic of every atom. Each atom has its own set of lines. So the question was to understand why these lines. And they had at that time an answer, but the answer was a model created by Niels Bohr many years before that worked for the hydrogen, and the model was like this. The atoms are made of a nucleus in the middle, and there are electrons describing perfectly circular orbits around the nucleus, and the radius of these orbits are very, very precisely determined by some laws, combining laws of an initial quantum theory and laws of classical physics. So they explain the lines as emissions of energy when the electron goes from one level to the other. So for instance, they explain the red line in the right-hand side as the transition between the third level and the second level. And then the green light, the transition between the fourth and the second. It was super nice, actually, for this. Niels Bohr got the Nobel Prize. But there was a problem. It just worked for the hydrogen. It doesn't work for other atoms. In particular, if you go to the helium, you have a different signature. And then is why this one? I mean, because the old theory didn't work here. So this was the problem Heisenberg was trying to solve. One night, he described this very late, 3 a.m. at night, he found a solution. Actually, he found a mathematical scheme that reproduced the lines. And then it was really shocked. The mathematics fits with the experience. And then thinking how he managed to get this perfect match, realized that this perfect match happened because he decided not to talk about orbits, not to talk about particles moving in orbits. The problem, as I said, of the model of Bohr is that it worked just for the hydrogen, but not with atoms with more electrons. There was another problem. Each of these lines had a different intensity. Bohr's model didn't explain the intensity. Also, when you have better machines, better spectrometers, you see that some of the lines split. Bohr's model didn't explain the split. And mainly from the theory point of view, Bohr's model was a mixture of completely different ideas. On the one hand, there was quantum intuition, some laws about the relationship between energy and frequency, but on the other hand, there was classical laws about how planets are moving around the center of the sun, for instance. But the point he realized, Heisenberg, I mean, actually, after the 10 days, he moved back to Hamburg, talked to Wolfgang Pauli, then moved back to Göttingen, where he was working under Max Born supervision. And around July the 9th, he realized what he did. And he wrote a paper. And this paper started like this. Well, he first described the situation of the search of the explanation of the lines, and then how desperate they are, because there are many people trying to understand what's going on. And they said, in this situation, it's sensible to discard all hope of observing hitherto unobservable quantities, such as the position and period of the electron, and to concede that the partial agreement of the quantum rules with experience is more or less fortuitous. Instead, it seems more reasonable to try to establish a theoretical quantum mechanics in which only relations between observable quantities occur. Heisenberg is proposing here physical theories built only on things that you can observe. And what you can observe in these experiments are the frequency or the wavelengths of these lines and the intensity of the lines. So he said, let's base everything on that. Because you cannot see the position, you cannot see the velocity, you cannot see the orbit, the electron. Okay? And actually start suggesting that the view of an electron orbiting a nucleus is a wrong mental picture. And because of that, he considered just the transitions between energy levels. He organized these transitions into a scheme, into a table. He associates an amplitude, which is something related to the intensity, the brightness of the lines, and he just look at the wavelengths or frequency of the lines and managed to reproduce the signatures of the atoms. It was obviously something important. Wolfgang Pauli immediately realized that cannot be by chance that you get the right answer. Okay. It worked. It worked for the helium, and has been working again and again and again, as we will see. Immediately has been working in a huge diversity of phenomena. These strange rules he wrote down that night in Helgoland work. And I've been working for 100 years. But there is a problem. Probably the person who verbalized better this problem was Richard Feynman, who in 1964, in a conference, I think in Cornell, in front of an audience of young students, said, I think I can safely say that nobody really understands quantum mechanics. People laugh, as some of you are laughing today. Next year, Richard Feynman got the Nobel Prize in Physics. And in this speech, he said something else. He said, we don't understand, and you shouldn't try to understand. Because very bright people have been trying to understand this for dozens of years and failed. So don't waste your time. Do not keep asking yourself, how can it be like that? Don't do that. Don't do that. Then Many people ask, well, what is the meaning of understanding? Well, of course, the answer depends on, but for Feynman, there's a lot of evidence that for Feynman, understanding meant something very specific. For Feynman, understanding means reducing whatever thing to an explanation that the freshman can understand. People that is not a scientist can understand. If you cannot elaborate whatever you want to tell in that terms, this is because you, not the freshman, don't understand. So it's clear what Feynman meant. And that's 1964. But this year, because of this 100th anniversary, the journal Nature conducted a survey over 1,101 physicists selected from people that have published papers in quantum physics in the last years, asking many questions that we will approach in these lectures, and the conclusion is clear. Physicists still don't understand quantum theory after 100 years. So this is our plan. First, in this lecture, I will try to solve the main problem of understanding quantum physics, namely that what most people think quantum physics is completely wrong. People think that quantum theory is a theory about cats that analyze particles that can be here and there. And it's not that. Actually, it's completely different than that. So therefore, if we want to understand something, we have to be very rigorous and very serious about what we are trying to understand. So apologize in advance, because this first lecture is going to be traumatic for all of you who never suffered an introduction to quantum theory. And it's traumatic on purpose, because I want you to experience what every student in the last 70 years experienced when he's exposed to quantum theory. And I try to be very, very rigorous in the words. I try to be very precise all the time. So I think I explain even better than most textbooks, but better means in a most honest way. And we need to go through this trauma. We have to, because whatever explanation is going to be an explanation about why this set of rules that we call quantum theory work. The second lecture today in the evening is going to be completely different. It's going to be very funny. Typically, people is very excited about that, because it's about how human beings have been reacted during the last 100 years versus quantum mechanics, how they face these strange rules, how they try to make sense of them in a completely different ways, and why. What are the key problems that force completely different interpretations of the same mathematical rules? The problem is lecture 3. In lecture 3, we start trying to do what is impossible, namely understanding quantum theory in the sense of Feynman. We will exactly ask what Feynman prevent us to ask ourselves. How can it be like that? Why? How is nature working such that we get, when we apply these rules, we get the exact lines? And it's going to be long, it's going to be traumatic, but in a different sense. It's going to be because I want to be rigorous. I don't want to skip anything in this explanation. Okay? And then at the end, we try to really provide an explanation and solve all the problems and all the issues that justify the different interpretations in the second lecture. So that's the plan. Lecture 1, welcome. Why quantum mechanics is the most useful and powerful theory? Well, because it makes strictly accurate predictions. But not just about the lines of the atoms, about a broad range of phenomena, completely unrelated phenomena. In principle, that is the main message here. And involving completely different physical systems under completely different interactions, and systems having completely different ranges of length, mass, energy. So let's start. What I mean by a physical system. A physical system is a small part of the universe that presumably you can isolate, at least conceptually, and in which you can perform experiments. Then what is quantum mechanics? Well, it's a physical theory that allows you to make predictions. But first important point, there are predictions about certain type of experiments. And these experiments involve interactions between some physical systems and some devices made out of physical systems, very complex devices that we refer to as measuring devices. And physical systems on which quantum mechanics applies successfully are elementary particles, atomic nuclei, atoms, molecules, ions, whether individually or forming ensembles like atomic gases or Bose-Einstein condensates or superconductors, all of them. Actually, quantum mechanics is behind the standard model of particle physics that classifies all the matter particles, quark, that are the green ones, sorry, the orange ones, and leptons, the force-carrying particles, the bosons, including the photon there in blue, the Higgs boson. I mean, the best classification we have about forces except gravity and matter particles after 100 years. But quantum mechanics deals with completely different ranges of length. It works, makes predictions on quarks, it makes predictions on protons, it makes predictions on nucleus, it makes predictions on atoms, it makes predictions on the electrons. It is behind chemistry. The whole periodic table is explained, in a sense, by these rules. It is behind molecular physics. But it's behind many, many disciplines. It's behind quantum chromodynamics, which studies the strong force between quarks, nuclear physics, which studies atomic nuclei and the elements, quantum electrodynamics, which studies interactions between light and matter, atomic physics, molecular physics, solid-state physics, condensed matter physics. And more recently, there are more disciplines based fundamentally on the same rules. Quantum information, which uses quantum mechanics to obtain new ways to process information, including quantum communication. Quantum sensing, which uses quantum mechanics to improve the accuracy in measuring and interacting with the world by detecting very small changes that cannot be detected with previous technologies. Quantum computation, which uses quantum mechanics to find new ways to make computations. Quantum simulation, which uses something I mentioned before, something that is very strange, I said. The fact that completely different systems follow exactly the same rules. And this is super useful because then some of these systems are interesting for pharmacy, for making materials and so on, and they're impossible to simulate in standard computers. But then you think, well, if these systems are behaving, following the same rules as these other systems I can control, why not using these other systems to simulate them? And this is exactly what we are doing in quantum simulation. But in a sense, it's a completely different sense of simulations as in classical simulation, because it's really a perfect mapping between one system and the other. A mapping that we don't really understand why happens. Okay? So quantum mechanics is everywhere, or in many disciplines. Famously, these days, in quantum computers, which are these typical machines, I should mention at this point that what you see, it's so impressive, is a fridge. The quantum computer itself is a small chip inside. Economy. People talk about the impact of quantum theory in economy, but actually the only actual trustable research was charged by a committee and was performed by some national lab in the United States. It's entitled "What Fraction and the U.S. Gross National Product Makes Use of Devices Invented as a Result of the Success of Quantum Theory." And it is very old. It's 1983. And at that time they said 23%, but probably this is not true. This is very low. This is 1983 is substantially larger because we are talking about transistors, we are talking about lasers, computers, TV, nuclear energy, biotechnology-based pharmaceutical, agricultural products. And all these things have experienced an expansion, a brutal expansions. All planes work because they have inside transistors and chips and machines. So if you want a number of what is the impact of all these things today, it's more than 50% and growing. But the most interesting thing is kind of this diagram, is the astonishing broad range of scales in which this works. So in principle, it works from quarks to relatively complex molecules and condensates and things like this. And it's a general opinion that quantum mechanics should work even beyond there. And there are people talking about quantum mechanics of black holes. There are even people talking about the wave function of the universe. But I am conservative, so I stopped the red line, which marks the application of the truly places in which quantum mechanics really work at big molecules. And one of the things we will try to answer is whether there are limits and why. And now the problem. The problem is a real problem. It's happening, has been happening for 70 years. Is the moment you receive a quantum mechanics lecture for the first time, and now the problem these days is the opposite, is the problem when you teach quantum mechanics for the first time. Because as a teacher now you experience exactly like this Harvard professor is describing. He said, when I teach quantum mechanics to students, they are expecting me to talk about waves moving in 3D space. And when I saw then the axioms, a lot of them are very disappointed. They are like, but where is the picture? Isn't it like there's an electron as we draw before and emits a photon as we draw before? And I'm like, well, the textbook axioms don't really talk about an electron here emitting a photon there. According to the axioms, that's just added for color. We draw pictures of electrons emitting photons just to help tell the story. But none of this is actually legitimate by the axioms of quantum mechanics. Some colleagues even said, all of these pictures are nonsense. So what are the axioms you receive, you are exposed to, you have to learn? Well, to understand what is quantum mechanics, I found something extremely helpful, which is a kind of divide and conquer strategy, because quantum mechanics has two layers. There's a first deeper layer, which is essentially mathematics. It's an abstract probability theory that I typically call quantum probability theory. And you can study this as detached from physics. It's very nice. It's a very nice exercise. But then you have a second layer in which you really add specific tools and physical ingredients that you need to model particular problems in physics. And together, these two things is quantum mechanics. Why is this helpful? It's because most of the problems we face are in the first layer, if not all of them. So we will focus from this moment on the first layer, this abstract probability theory. And this abstract probability theory contains axioms, but basically it tells you how something called states that I will define are mathematically represented in the theory, how something called reversible transformations are mathematically represented in the theory, how observables are mathematically represented in the theory, and then finally it tells you how to combine these mathematical representations to make predictions. I will spend half an hour explaining the details, but it's just this, and no more than this. Okay? If you ask me what else is missing, it's a good question. What is in the second layer? Well, in the second layer we have many things, but basically there are many things that allow you to deal with a specific problems. For instance, in the first layer, you associate with every observable mathematical object. However, the first layer says nothing about how you should construct this mathematical object for a specific physical problem. Then, in this second layer, we have a set of tools to make this transition. Okay? We look at the classical way of attacking this problem, and we kind of transform each of these, for instance, Hamiltonians, into the quantum version of that. But the point is that this is in the second layer. The Schrödinger equation, everybody have ever heard about the Schrödinger equation, but the Schrödinger equation is in the second layer. I mean, because in the first layer, you only have that every symmetry in the state space corresponds to a particular object, but this layer says nothing about how you should construct this mathematical object for the interesting case in which you're talking about the time evolution of a closed physical system. Okay? And then this is done in the second layer, and this leads to the Schrödinger equation. Another example is Planck's constant. Planck's constant is everywhere in quantum physics. I mean, it's a constant of action, product of energy and time. Okay? And it's quantized according to all quantum mechanics and has a specific value in this universe. Okay? But it's an addition to the abstract probability theory that is in the first layer. So what I'm saying is that I won't talk about any of this. I will focus from now on the first layer. And then I have to explain the first layer, operationally. Very detailed one. So when I said state, you are not misunderstanding me, because state means something very, very specific. And I mentioned before that quantum mechanics deals with a particular kind of experiments in which you have essentially two phases that we will call preparations and measurements. So what is a preparation? Preparation is a reproducible experimental procedure that involves an interaction between a physical system and a device consisting of another physical system. I will represent the preparation by a box emitting an arrow. The arrow is supposed to represent the physical system. Okay? I will be more specific about what are we asking about the box. It's not any box. Then you have something called reversible transformation, that is something that changes something in the physical system, and is reversible means that you can't reverse. So if you apply the transformation and then the reverse transformation, that's equivalent from the perspective of the experiment, is equivalent of doing nothing. And then you can combine a preparation, a transformation, then create a different preparation. Okay. But then we have the core. The core is what you do after the preparation, the measurement. And a measurement is an interaction between a physical system coming from a preparation and a device, which will consist of many physical systems. And it's an interaction that is very special. It produces an outcome, a click, a light flashing like here in the drawing, a spot in a plate, something that is classical, which means something that you can copy and transmit to other people. But in principle, it leaves you with the option of keep making more measurements on the same physical system. Okay? That is what is reflected in the arrows in the right-hand side. Of course, in many experiments, this is not the case. In many cases, to get a click, you have to destroy or capture somehow the physical system. For instance, to make a spot, you need the atom to accumulate in a plate, something like this. So you cannot really use this atom and make more measurements on the same atom. But in other experiments, if you put more careful, you can do that. You can keep asking questions, making measurements on the same atom. Okay? But what is really characteristic is that in addition, these questions do have an answer, do have a click. And this click belongs to, that's super important, to a specific set of possibilities. That's why I'm putting two lights up and down. There's just two possibilities. Either you get a flashing light up or a flashing light down. But it's important. In principle, every time you inject a physical system, you get a flashing light. Example. We will use this example all over the lectures. Is the famous Stergelac experiment. In the right-hand side, in the left-hand side, you have an oven full of silver atoms. You heat the silver atoms, you make a hole, so from this hole, silver atoms are released. I'm doing just drawing in the air. Okay. Then you have some slits that collimate, that selects a beam, whatever, of silver atom, and then you put a magnet with a specific geometry, and after this magnet, you put a screen. And in the experiment, you can change the orientation of the magnet, and you register what is accumulated in the final screen. And this is the original experiment. What you get is what you see in the right-hand side. When you put silver atoms, you get basically two lines, one in the right, one in the left. While for other atoms, let's say palladium, you don't get that. You don't get this split. You get single line. So it's important to understand why it's split in two. Where is the preparation? Where is the measurement in the Stergelac experiment? Well, you can draw the line here. For instance, here is a little bit more complicated. in the sense that you also put a magnet after the first preparation, and then you block one of the possibilities, so you just allow the other possibility to happen. This by itself constitutes a preparation. And then the measurement is a second magnet and the screen. Then you can change the measurement by rotating the second magnet, okay? Or you can really complicate the preparation, adding a second magnet after the first and before the third magnet, okay? But at the end of the day, you are having something like this. You have a set of preparations and a set of measurements. This is the important part. Because then what you do is the following. You face each one of the boxes in the left-hand side, each one of the boxes in the right-hand side. Facing means you do it like this. You prepare many systems using one of the preparations, and you measure them using one of the measurements. And here, you expect a very specific behavior. You expect that, for instance, the upper outcome happens with the probability 20%, and the lower outcome happens with 80%. Today, tomorrow, and in a week. If the boxes don't behave like this, you throw out the boxes. This is just a theory about boxes that behave like this. Clear? That's important. You focus on that. Well, but you do this with all possible combination of boxes. So at the end of the day, you create a table like this, in which I put numbers, which means the probability of one of the two outcomes. Obviously, the probability of the other outcomes is 1 minus the probability that is in the table. Good. And then you define a state. The key concept here. The most misunderstood concept ever. What is that? Look, the state is just this. Two preparations may look different because they are represented by boxes of different colors, and yet lead to the same probability distribution for any measurement within a given set of measurement. In this case, we say that the two preparations are equivalent, and the relation of equivalence between preparations defines what in mathematics is called an equivalence class. Each of these equivalence classes is called a state. Meaning, here you notice that if you just look at the numbers, there's no way to distinguish the red box from the yellow box from the blue box. So, with respect to the measurements in the upper row, we said that the three boxes are actually preparing the same state. And we are talking about a theory that uses exactly this language and uses the name state exactly with this sense. All physicists will agree on that. For some physicists, there's more than that. For some physicists, there's even less than that. But I think we agree that state operationally is something that is defined this way. But this is just the beginning of the story. Because you have the measurements. Then you define something, this leads to a classification of all the boxes into states, and then you have the measurements, and then you want to classify the measurements as well. And then you invent something that is called observable. Because the logic is similar. Two measurements might look different and yet lead to the same probability distribution for any preparation. In this case, we say that the two measurements are equivalent, and we call each class of equivalence an observable. For instance, here, you notice that the orange and the green box actually produce the same probability distribution for any of the preparations you have. So you declare that both are measuring the same observable. And we are talking about a theory in which the names state and observable operationally mean exactly that. But then the biggest misunderstanding in the way we talk, explain, teach quantum mechanics is in what we call a quantum system. 99.9% of the textbooks, videos, and conference uses the analogy an electron is a quantum system, a silver atom is a quantum system. Nope. From this perspective, that is simply incorrect. Then, now you have a classification of observables. So, collectively, you have observables and states. A quantum system is precisely defined by two things. First, the set of states, and then the set of observables. So you need both. You need a clear operational description of what are you preparing and how you are preparing versus what are you measuring and how you are measuring. Together, when you have all this information that allows you to do this boring exercise of deciding when two states are the same, when two preparations are the same, when two measurements are the same, then, and Niels Bohr would say it, and I would say it, and only then, you declare that you have in front of you a quantum system. Many people would object that because said, well, we presume that we know, especially in high energy physics, we know the measurements potentially we can know, so we can talk about counts as quantum systems. Not really. Not really. In a deep, precise sense, not really. But in any case, we agree on this is a theory about probabilities, and when we talk about probabilities, we talk about probabilities in this precise sense. So, an ideal experiment in quantum mechanics, possible but super difficult to make, but now we can make these experiments, is something like this. You prepare a state, actually a state that cannot be decomposed as convex combination of other states. We call it pure. We say it maximal informative state, something like this. Then you applied just to show power a reversible transformation, so you really transform the state in a precise way you want, and then you perform a measurement, which is a measurement that is non-destructive, okay? In a sense that allows you to keep measuring more, to keep the experiment, and not only that, it's ideal, which means it's minimally disturbing in a sense that I will explain and will be super important in the third lecture. So this is dreamland for a quantum scientist. But then hell for a quantum theory student, because he said, okay, axiom number one. Axiom number one is how the states, in the sense I mentioned before, are mathematically represented in the theory. Ready? Take notes. Every quantum state of a quantum system is represented by a density operator rho in a complex Hilbert space. What is a density operator? Well, it's a self-adjoint or emission. If you are in finite dimension, it's positive, meaning that is of unit trace. They're shocked. But actually, the most shocking part is not in most of the textbook, but it's the most shocking part, which is the second. Any density operator, anything with these mathematical properties, represents a quantum state, meaning in principle you can go to the lab and prepare that thing. It's a perfect match between mathematics and physics. This is the most let's say, general formulation of this first principle, but the simplest formulation is interesting for us. Every quantum state of pure quantum state, maximum informative power, is represented by a ray, a vector, in this complex Hilbert space. And any ray represents a state, a quantum state of maximum information. Okay? And this Hilbert space is called the state space of the quantum system. I forgot to mention that, okay, Heisenberg came back to Göttingen, and he was looking for job opportunities. He had an invitation from Cambridge, so asked Max Born to leave for some weeks to Cambridge, but Heisenberg left the paper to Max Born with these strange rules of multiplying things and getting the tables. And Max Born took them, and in 2 days he said, well, wait. This is matrix multiplication. Göttingen is the city of David Hilbert. So he said, we know this mathematics. We see this mathematics before. And it's kind of a shocking coincidence that the house of David Hilbert and the house of, which is older, was substantially older than the house of Max Born, are separated by a block, right? It's like, what? So you have Hilbert spaces here. And then second axiom is about reversible transformation. Reversible transformation are associated to symmetries. Symmetries in the state space. A symmetry is something that remains unchanged when you make a transformation. If I rotate a particular angle, you don't see the difference in the figure there. So that's a symmetry. Okay? And okay, wait. The second postulate of quantum mechanics is also called Wigner's theorem. It says that every symmetry of the quantum state space is represented by a unitary or anti-unitary operator, and the other way. Good. You have a mathematical object. The definition of what is a unitary is there. And then about ideal measurements of observables. The way ideal measurements of observables is represented in the theory, and ideal measurements here is for the first time defined, although you don't have yet ingredients to understand the definition. An ideal measurement of an observable is one that does not disturb any compatible observable. We'll explain exactly what is that, because it's super important. But what is represented in the standard quantum mechanics is this ideal measurement of the observable, and is represented by a self-adjoint operator. The only possible results when measuring an observable are the eigenvalues of the operator, and then the magic again. Any self-adjoint operator in that Hilbert space represents a physical observable. Perfect match. And now the end of the party. Okay, you have mathematical objects representing these operational things, preparations, reversible transformations, and ideal measurements of observables. For what? Okay, the main purpose is to compute with these objects the probabilities of the different outcomes. Given an initial state, if I measure this observable, what is the probability of obtaining this outcome, or this outcome, or this outcome? And this is given by a rule that you have in equation 43. Okay, it's the trace of the self-adjoint operator, in this particular case, the projector that represents the outcome you are getting, what you measure in the observable you are observing, times the density matrix that represents the state. You get a probability. And the probability is related, for instance, to the intensity of the lines. And you get it right when you apply that. That is Max Born rule. He got the Nobel Prize for that. But you can also ask yourself, okay, In this case of ideal measurements, what is the quantum state after the measurement? How the quantum state transforms from before the measurement and after the measurement. That was really solved wrongly initially by von Neumann. Until 1951, no one really realized that there was a mistake in the books and correct the mistake. And the right formula, the right correction is equation 44, is Gerhard Lüder's. But this is kind of shocking and super important because we're talking, typically we said that quantum mechanics was done in 1927, and it's not really correct because a very important aspect of quantum mechanics, this transformation, was wrong in all the books until 1951. Good. Then you have the most famous way of this last postulate, in case your state is pure and you are measuring what is called a maximal observable, and that is, well, a maximal observable, then the same rules have a very nice mathematical representation, what is respectively given by equation 45 and equation 46. And yeah, I won't enter into the details. So, what are you looking? Stop. It's over. That's it. That's quantum mechanics. This is just an example how it works, but that's quantum mechanics, period. There's no cats, no particles here and there, no multi-universes. There's nothing like this. I'm not kidding. That's true. This is the whole quantum mechanics. I mean, this is an example. Look, now imagine here, this ball is a preparation. It emits physical systems, okay? And then the first box represents one measurement you do. X is this first measurement. The fact that X can take two values, 0 and 1, means that, well, I can make two different measurements, or 0 or 1. And then I produce an outcome, A. And the fact that A can take two possible values is reflecting that there are two possible outcomes in this measurement. And then, if I'm very good in the lab, I can perform a second measurement on the same physical system. I call the second measurement Y. Actually, I can choose Y to take two possible values, two possible measurements, again, 0 and 1, and then I produce an outcome, B, again, 0, 1, and then I run the experiment many, many, many times for the 4 different combinations of X and Y, and I collect the statistics, and at the end I sit down and said, okay, the probability of measuring X0 and getting A1 and measuring B0 and getting B1 is whatever. And I do with all the probabilities, and I create a table like this. Okay? Now imagine I do the experiment, you do the experiment, you get a table like this, and you ask Professor Kleiman a very simple question. I got this in the lab. Is it correct? Meaning, according to this beautiful theory called quantum mechanics, can happen, what is this pattern, this set of probabilities. And the best Professor Kleiman can answer is the following. Well, the answer would be yes, if there is a set of cells adjoint positive operator of trace 1 rho, and 8 projectors, blah, 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 such that 4 of them and 4 of them commute, and these 2 are orthogonal sum the identity, and the other 2 are orthogonal sum the identity, and then with these components, whenever you take traces and so on, you manage to reproduce. Then, this can happen. If you cannot do that, if then it's impossible in nature. Next. Can you do it better than that? No. And actually, as we will mention in the last lecture, at the end, even that question is not easy to answer yes or no. I mean, it has been recently proven that might be undecidable. I can get a table like the one in the right. I mean, I said, okay, is it possible? And you can never answer, even knowing the theory. Whatever. The other day, I have a discussion with a colleague because I said, Feynman said, nobody understands quantum mechanics. And he said, yeah, we know quantum mechanics. We know how to compute. We know how to calculate everything. We know how to do that. We know this. We know that there's a one-to-one correspondence between what in principle can be done in the lab and that. Do you understand quantum mechanics? Do we understand quantum mechanics? So, thank you for coming to this first lecture. Next lecture will be in the evening and will be about why physicists disagree and what the problems behind these disagreements are. Thank you. It's supposed to be traumatic, so I met it. I'm happy with that.
I will break the ice. I'm in philosophy and not in philosophy of science, but I was, you struck me like this when you explained the story of why the question, the initial question, we will stick to what is observable. So let's forget about, in my view, there was kind of I kind of feel a paradox. What we usually connect to what is very strange quantum physics, very strange, unobservable, something that happens but we cannot explain, Actually, it took place, the initial cause was the fact that a physicist just said, well, we will stick only to that which is observable. There's kind of a paradox in the story here. That I didn't know, so that was kind of we stick to what is observable, and then that produced a line of physics.
But even that is a narrative. I mean, being honest, I try to emphasize that the story is like one night playing with some tables, Heisenberg managed to get the lines, the correct lines and the correct intensities. And so he was shocked. And start thinking, what I've done? What I've done? And then moved back to Hamburg, said, Wolfgang, I have it correctly. What I've done? And Pauli said, whatever you did is amazing. And then take the train back to Göttingen, said, what I've done? And finally in July I said, oh, what is clear that I've done is renounce to the orbits, renounce to, and start creating a narrative. It's a 23-year-old person trying to convince the whole German physicists that this is necessary. So he said, he creates this narrative, we have just to focus on the observable. And we're still in this narrative. And anticipating what is going on in the next lecture is, what is going on is people trying to put pictures behind this narrative. Because this narrative is not compelling for most of the people. And, or not enough for some of the people. But as also we try to prove is sufficiently good for most physicists. And we are stuck in that situation. But I insist on the narrative. I myself is Heisenberg put weeks of thought trying to follow his own mental process during Helgoland. And it works. So always the same reaction is, who cares? If it works, who cares? You don't care about how your car is working. You care that it's working. So you leave the problem of fixing the car to people who knows how the cars are working. And you live your life happily. And that's what society does with quantum mechanics as well, and that's what physicists does themselves. They expect there are some physicists that work on foundations that care about this problem, but they do their job. And has been like this for 100 years, and yeah, we're doing our job.
Thank you. I'm an engineer, so I'm neither a philosopher nor a physicist. So I come to this house to understand a bit philosophy, and I come to your lecture to understand a bit physics, and I'm completely lost as usual. So that makes sense. Question is, if we bridge a bit philosophy and quantum physics, how correct is, in your opinion, a sentence like, quantum physics is just epistemology and it's not ontology, or we don't care about ontology?
I cannot answer this question without spoiling the final thing.
Oh, sorry about.
So, but you will start getting insights about that in the second lecture, because I will ask myself a lot of questions after the second lecture, and the way I'm facing the third lecture. And hopefully, at the end, you will get the answer, the full answer in the fourth lecture. So I cannot yet answer that. I mean, the narrative of my own, the design of this lecture is intentional. I try to be, let's say, objective about what is going on now, about how different people face the same thing, and what are the standard objections to any of these views. And then, modestly, I will try to solve them all. And in doing that, I will answer your question.
Thank you.
Yes. Sorry for not answering now.
Adán is accusing me of having oscillating opinions, and I will use this now. So currently I'm teaching mechanics to explain the hydrogen atom, right? And the spectrum of the hydrogen atom mostly. So how would I ever do this with just talking about state preparations and measurements?
I mean, you explaining the hydrogen atom. You go to shift, you explain. I mean, you have to design the Hamiltonian. You have to find the Hamiltonian, and then you run the theory. The key thing.
Then I have the spectrum of the hydrogen atom already. I have to know it has to have discrete spectrum.
Yeah.
Because I start that's the wave function of two particles or charged. So I put constants which I have of the system I want to describe for whatever reason, which I have from other experiments. I'm really it doesn't really work. So I put in my ideas how I conceptualize, and then I start to calculate. It's not that I talk about state preparations and the experiment doesn't even work like this, or what would you say?
But what are you? I mean, at the end of the day, you're computing probabilities of this energy level, this transition, and this is what you want. I mean, that when you said I explained the hydrogen atom, if I'm not explaining the hydrogen atom, you are explaining transitions and things you see from the hydrogen atom. This is what we talk. And then you design, you get, as you said, previous knowledge, you get somewhere else about the energy levels, you design the Hamiltonian, and then you solve equations, and then you get probabilities of transitions, depending on what you want to hear about the hydrogen atom. But all the time you use this language of wave function to clarify this. Wave function is state. Is the old-fashioned way to say exactly what I'm calling a quantum state, and I'm represented with these objects. Okay? And whenever you said there's a wave function, it's because there is a way to prepare, a way to say, is this wave function versus is there other wave function? And what you study is how this wave function evolves and give you answer about energy levels, about emission, and so on. So we have to do. I mean, we have to do that, but we never cross that. I mean, you go to the shift, and it's amazing how the shift book is a famous book in quantum mechanics, how the hydrogen atom is explained, described. What is amazing is how clear is the connection between the elements that you can visualize about the atom and these objects there. But you are always stick to that. Whenever you have, the statement is really loud. Whenever you said, I have a wave function, presumably you know how to prepare. You know the starting point. Moreover, whenever you have a wave function, also you have the target, you know the measurements you are talking about for this. If you ask me, and out of the record, I mean, a question typically is this wave functions associated to the system, for instance, to the hydrogen atom? Most people will say yes, every hydrogen atom has its own wave function that tells you all the possible experiments you can perform on the atom. But honestly, it's not clear to me. For each part of the wave function in their language, you have to design an experiment. And most of the experiments you can do on the hydrogen atom are mutually exclusive. So presumably you can extract all the possible information of all these mutually exclusive experiments from a single super big wave function, but nobody has done in the books. Okay.
So thank you very much for the talk. I'm a chemist. I'm trying to explain something about quantum chemistry in first course when they arrived just from the high school. So I was trying to figure out how can I explain hydrogen atom using, okay, all these new concepts in the sense that they are new for them, but also the word wave function. So maybe you can go deeper inside everything, but I have chemists, and they hate me every time I say wave function. And every time I try to explain that, okay, they are numbers, it's nothing to do with cat, and they hate me. So
yeah. I mean, I have just a practical advice. I mean, start with something they can follow, namely Bohr model. Bohr models you can visualize, you can do things like this. There's a jump, there's a transition. Look, for whatever reason, only these orbits are nice, and and there's transitions, and look, there's a perfect correspondence, and this always happened because energy is quantized, and also there's conservation of quantities and so on. And the moment you got them, you said, you know, everything is wrong.
Yeah, I will use this. But yes, but I am, as a chemist, I need wave functions.
Yeah, we all need
And I
wave
need-
functions.
yeah.
But the emphasis of this dramatic lecture is when you said, I need wave functions, you need this. You need something that allows you to ascribe this wave functions, which means this. You need operationally to define. It's kind of the question of Professor Kleinman as, okay, where is the preparation? Where is but there is there. Somehow implicit is there. I can do. There's an assumption of what I prepare. That's why I can start talking about wave function. And then you have to follow the standard ways physicists have developed about that. I mean, changing the tone of your voice when you said amplitudes of probability. Check the internet. Amplitudes of probability. It's like black magic. Because they said they are not probabilities. You know that? They're amplitudes. And they do, and we've been doing for 100 years. And it's really from the sociological point of view, really is really interesting because it's how human beings are trying to explain something that is super important. We're teaching chemistry, and we will be teaching chemistry forever. And we have to, because that things explain chemistry. Sorry for being everything. There's no option. There's absolutely no option. This is what we've been told. Again, in a sense, I will try to answer your question at the very end.
Okay.
Because basically the question is, these rules work. Have been working for 100 years. Notice how it works. You have to teach them why they work, how they predict the right thing all the time. And then you have to try to explain why, where this, how nature is really working such that these laws happen to be the correct ones. And this is what I'm trying here. So you have these things that work in all the atoms, all the high energy particles, all the molecules, solid materials, everywhere, quantum computers. And they are completely different things, but they follow exactly the same tables of numbers, mathematical objects. So it's better not to go one by one, trying to picture there's an electron flying here, but rather try to find why in all these cases happening, what is common to all these cases, and start playing with the hands, sort of suggesting an answer to you, find an ontology that explains at the end of the day the numbers. And there are many ontologies, so you'll see plenty of ontologies this evening. Yeah.
Thank you.
Thank you.
Any other question?
Thank you for your lecture. I beg your pardon. I'm an engineer as a colleague, so my question will be something different. Let's assume that now we say we know more or less the micro-universe, and we know also the Big Bang and the big universe, but it seems we need something that brings them together. I remember in the first slides you said a system is part of a universe, of the universe. And in the lecture 4, you say, we try to explain how nature works. Why you say nature and not the universe? Maybe this is a philosophical their way, but you understand?
Yeah, but
Thank
in this particular case, in this particular example you're showing, because I wanted to say something larger, is how nature works in this particular experiments. So it's not the universe. If I put the universe work, I sort of suggest something different than when I say nature. And this is intentional. And this extension is because to explain the last thing, I don't need the universe. I don't need you to think about the universe. I need to think about something, let's say, small, particular, of some particular pieces of the universe combined in a particular way, very particular way. I want to understand how their nature works. And if I said universe there, I am getting you the wrong picture, because it's not the universe. There are partitions of the universe, each of them intentional, each of them with their own features, combined in a particular way. And when I said universe, the universe is an entity alone, and I thought I would get the wrong idea if I use universe rather than nature. Although nature is not the right thing, as we will see eventually. Okay, sounds silly, but it's kind of intentional. Thank you for the questions. You will, again, sorry for that. You will see the why at the very end. We're still in the traumatic era. I mean, this is the dark. Well, the dark times are about to start now. Now it's it. So eventually you will understand my choices.
Okay, hi, thank you for the talk. I have a technical question. So I'm also an engineer, so maybe it's something that physics already know, but so this discrete state definition works nicely when we are measuring spins up or down or this kind of stuff. But when measuring positions, for instance, that can take continuous values, how this state definition works? You set ranges or how?
The same way. I mean, okay, the same way. You can have an underlying continuous quantum system in the sense that is represented by a self-adjoint operator, infinite dimensional Hilbert space. And then you can do, the practical thing is you discretize. When you set position, you create windows of positions, right? But at the level of the mathematics, the underlying Hilbert space is infinite dimensional. Also, you still have 2 flashlights or 3 or 4 or whatever number. So this is what you do. And then you can think about continuous, mathematically you can write down also continuous outcomes. I mean, and technically the definition works because whatever set of outcomes we said should be, can be put in one-to-one correspondence with the real numbers. And real numbers are also as infinite as. Okay, so it's done. Actually, that's why I use self-adjoint rather than Hermitian. Self-adjoint is for infinite dimensional, covers everything. Hermitian is all the matrices are finite dimensional, and yeah, most of the quantum computation is just relatively small matrices, and that's it.
Okay then. We don't know what quantum physics is about. Maybe we do not understand what quantum is about. What we do know is that we have to wait for the following lectures to get a better idea. So I invite you to resume this seminar this evening at 4 p.m. and the following 2 lectures tomorrow. So thank you very much for this first lecture. We see it again.